Hello, the work I'm presenting today focuses on the growth and characterization of novel iridium and chromium oxides. Chromium dioxide is a half metal with high ordering temperature, very small coercive field, and a large magnetic moment. And because of these properties, it's a material with great potential for the development of new spintronic devices. However, chromium dioxide, which crystallizes in the rutile structure, is also a thermally unstable phase with a tendency to decompose into the antiferromagnetic and more stable chromium-2 oxygen-3 phase. In addition, conventional film growing techniques such as sputtering or PLD haven't succeeded yet in synthesizing this compound. This is clearly a major drawback for the development of spintronic devices. Here, we propose diluting or doping as a new route to stabilize the chromium 4+ ion in the rutile structure. This route could prove to be also useful to tune the magnetic response. It is to be noted that chemical doping has been barely and only recently explored. Therefore, within this context, in this work, the growth of iridium-doped chromium dioxide is explored. The formation of a stable iridium and chromium oxides with rutile structure hasn't been reported yet. However, it can be expected based on the fact that iridium and chromium conform the so-called Hume-Rotary rules for the formation of substitutional solid solution phases. In addition, iridium has been chosen as the dopant element because it may lead to the control of the magnetic anisotropy. Compared to the localized magnetic moment of rare earths, the more extended 5D orbitals of iridium may prove to be more efficient in induced hardness. In addition, in these oxides would combine in a single material the half metal character of the chromium oxide and the high spin orbit coupling of iridium dioxide. This could give rise to innovative properties and devices. Given the practical importance of sputtering for the growth of films in favorable industrial conditions, the films were grown by sputtering. More in particular, the iridium and chromium oxide films were prepared by conventional oxygen-reactive magnetron co-sputtering deposition on silicon substrates at room temperature and from metallic iridium and chromium targets. And in order to get polycrystalline samples, the as-grown films were annealed in air for 6 hours. As can be seen in the low right figure, single phase with rutile structure can be obtained for all the films with a content of chromium between 0 and 0.7. In other words, the reactive sputtering has shown to be to succeed in stabilizing chromium in the rutile structure. The analysis of the X-ray absorption spectra allow us to conclude that both the chromium and the iridium present a 4+ oxidation state. Besides, the presence of chromium-2 oxygen-3 can be ruled out from this data. And regarding the magnetic properties, as you can see in the top figures, in all the diluted films, there is a pronounced bifurcation between the field-cooled and zero-field-cooled curves. This behavior is very different from that observed in the parent compound, in the chromium dioxide, as you can see in the bottom left panel. The magnetization versus temperature curves present strong temperature dependence, which also depends on the chromium content. The maximum value reached by the magnetization increases with the chromium up to about 70% of chromium. After that amount of chromium, the system becomes mostly amorphous, and the magnetization decreases, as you can see in the bottom right panel. And something similar happens to the magnetic ordering. It increases with the chromium content and reaches a maximum at about 0.6, 0.7 of chromium content. So at room temperature, all the films are paramagnetic, but low temperature, the films, the diluted films present a ferromagnetic component. As you can see in the hysteresis loops in the right, the diluted films present a high coercivity. For example, for about 60% of chromium content, the coercive field reaches 4 Tesla. And again, this is very different from the behavior observed in the pure chromium dioxide, as you can see in the right bottom panel. This difference suggests that the presence of iridium may be responsible, at least partially, for the increase of the coercivity. And finally, the differences observed along the series allow us to conclude that it is possible to tune the magnetic coercivity by changing the iridium-chromium ratio. XMCD technique allows us to disentangle the contributions from the chromium and iridium sublattices. The XMCD signal recorded for the iridium edges reveal a sizable magnetic moment on the iridium ions. In addition, the fact that the signal recorded at both L2 and L3 edges is similar in size but with opposite sign indicates that the character of the magnetic moment is mainly a spin moment. And this is very interesting because it's very different from the typical large orbital magnetic moment found on iridium 4 plus oxides. An example of this is found here in green. You can see that the XMCD signal is very different, showing a different character of the magnetic moment. In addition, this suggests that the magnetic moment of iridium is induced by chromium, which is quite remarkable and surprising result for an oxide. As for the chromium sublattice, the similar size of the XMCD signal recorded at the chromium KH on both doped and undoped compounds indicates a similar net magnetic moment in the chromium sublattice for both systems. However, looking more in detail, we can see that the doped sample presents an extra feature that is not observed in the parent compound. This again suggests this can be associated to a iridium contribution, in turn associated to a chromium-iridium hybridization. So, to conclude, despite the difficulty on growing chromium dioxide by physical deposition techniques, a single-phase solid solution has been achieved by conventional reactive sputtering. Iridium, chromium, and oxygen crystallize in the rutile structure for an amount of chromium between 0 and 70%. Along the series, the oxidation state of chromium remains as 4+. And regarding the magnetic behavior of the diluted systems strongly departs from that observed in the parent compounds, chromium dioxide and iridium dioxide. In particular, by doping with iridium, the coercive field can be largely modified, achieving values up to 4 Tesla at low temperatures and even larger. The XMCD reveals a significant contribution of the iridium to the magnetic response of the films, and in addition, it reveals mainly a spin character of the magnetic moment, which is very different from that typically found in other iridium 4+ oxides, and strongly suggest that this iridium moment is induced by chromium. This is quite remarkable and surprising results for an oxide. So the work on these oxides has only started, and further work is needed to fully understand the magnetic properties of these systems. However, the results so far point to a very interesting playground with a great potential. And finally, I would like to thank my colleagues from the Institute of Nanoscience and Materials of Aragon and from the IPS at the Aragon National Laboratory, and all of you for your attention. Thank you.